Well, welcome everybody. I'm really glad to see everybody here. So welcome to the second in our new Office of Vice President for Research Symposia series. These symposia are an opportunity to connect experts in research areas across grounds and to highlight the work happening at UVA in many different areas. So look for more symposia coming in the spring of 26. I'm thrilled that we're featuring quantum computing among the first few events. And I want to thank Olivier Pfister and Stefan Bekiranov for submitting in these first events. So we had an open solicitation for topics for these symposia, and Stefan and Olivier led the submitted the topic of quantum computing. So why quantum computing? It's an emerging area of science with huge implications for other research areas. It's complex and evolving rapidly, and the goal of this symposium is to help demystify the technology and give us all a common baseline of understanding. I can tell you, I was an undergraduate physics major, and I went to a quantum workshop about a year ago, and it is a complex topic, but our speakers today are dedicated toward making it accessible to many people. It's a launch pad for collaboration. Quantum computing intersects physics, computer science, medicine, data science, engineering, ethics, among other areas. So we think that this will demand collaboration across these areas and more. And our hope is that many of you today will connect following the event and work together to bring your best ideas to light. The reception afterward is the perfect place to connect with a new collaborator. It's one way we can build institutional readiness and make UVA a leader in this space. So quantum computing is a major focus of the current US administration for funding. And we're hoping that by coming together around this symposia, we can take our shared understanding and move towards shared goals that can influence national agendas. I'm in it for housekeeping. So please feel free to come and go over the afternoon as you need to based on your schedule. We ask that you move toward the center of the aisles so it's easier for others to sit down and grab a seat. Please remember to silence your phones, and restrooms are down the hallway toward the library, and I think they're up on the second floor. The event today is broken into 3 sections. First, there will be 3 longer form presentations that include both a 101 look at quantum computing and some specific applications. Then we'll hear a round of 7 lightning talks with UVA experts and collaborators. And then lastly, a panel session with a Q&A to wrap up the event. So now I want to introduce our first presenter. Stefan Bekiranov is professor of biochemistry and molecular genetics in the School of Medicine. His research integrates advanced machine learning and quantum computing to develop predictive models for clinical outcomes and genomic functions, leveraging multi-omics, epigenomics, and single-cell data. So welcome, Stefan.
Thank you, Fred. All right, thank you, everybody. We're going to get going. All right, we're going to make this a Q&A. We're going to make this fun. There's going to be a quiz. Okay. Can you hear me? Okay, so put this in my pocket. Yeah, okay. All right. All right. So first question, I'm going to make this interactive. First question is, how many people know what quantum computing is, maybe work on it? Okay. How many people don't? Like really clear show of hands. Okay, that's pretty good. And then how many people have never taken a quantum mechanics class? Never. Like really never. Okay, good. How many people have not taken a class in linear algebra with complex numbers? Raise your hand clearly. Oh, wow, almost. Okay, so I can see that's actually really good. Okay, so, all right, so let's get going. So let me see, we just advance like this. And is this the pointer? Yeah. Okay, so we're going to cover gate-based quantum computing or discrete discrete quantum computing. You'll see there's a difference between continuous variable. So I'm going to give a brief introduction to quantum mechanics and quantum computing. And what I want you to do as we go along is raise your hand and ask a question. This is going to be like a class, and I might ask you questions. I like to make it interactive, especially for this. And I may not get to the second half, actually. So that's going to be a quantum machine learning application that we worked on. If we do, it's great, but what I really want to get to is the essence of what quantum computing is and set up the rest of the day. Okay, so now the only thing I ask too, this is gonna sound funny, but the only kinds of questions that I don't want to kind of respond to is how weird quantum mechanics is. The only reason is that can take up the whole time. So we're just gonna kind of focus on the quantum computing part. But I still want to give you an understanding. Okay, so let's start with quantum mechanics, okay, because that's the essence of this stuff. So let's say you have an electron, and it's being shot out of a gun, and you have an electron gun, and you have a wall where the electrons can't penetrate the wall, but they can go through these slits. Okay, now, I usually ask this, but for the sake of time, when you just think about classically what you'd expect ballistic transport like this. You might expect some bouncing off walls and who knows what. And so you kind of get a distribution of electron detections at this wall that look like this, in like this, and then maybe one big lump. Does anybody disagree with that? Like if you just shot BBs and electrons were like BBs? Does anybody say no way? Okay, that's not what you see famously. What you see is this. And this looks a lot more like if you threw a rock in a pond and you had waves emanating from the pond, and then when they hit the slits, these waves would re-emanate from the slits, and you would get constructive and destructive interference. You'd get parts where, like here, where the two parts of the waves come together at the top of a wave. You'll get sections where they cancel, where they destructively interfere, and sections where they both go very low. Okay? That's exactly what this is like. And what I'm going to kind of really make the case for is quantum mechanics is actually, when you take it at face value, not that hard to understand. It's when you try to reconcile it with the macroscopic world that it becomes a bit difficult. Any questions at this stage? Okay, fair enough. So what describes this phenomena? Well, with great accuracy, the Schrödinger equation does. Okay, and you may have heard of this equation. It's very famous. It's one of the fundamental equations of quantum mechanics, and we're about to celebrate 100 years of this equation. So basically, when you solve this equation for that problem, and then, so what are you solving? You're solving, this actually is something like the total energy. This is a del operator, it's a derivative operator, but think of it as p squared over 2m, kinetic energy plus potential energy. And it's acting on a function known as a wave function, okay? And this defines the evolution of the wave function. It defines the evolution of a wave that we solved for in that previous problem, okay? And I just want to point out something else first, that you can see there's no squared or cubed or anything in these psi's. This equation is linear in psi, and that's extremely important, okay? But remember, at the end of the detector, we don't really measure kind of waves lapping on the edge of this. We do measure discrete electrons, okay? So our current basic model is that that wave function, when you measure, collapses, and what you measure at the back end is the probability of detecting the electron. So what is this psi? What is this psi? Schrödinger didn't know when he actually came up with the equation originally. This psi, when you square it, gives you the probability of detecting the electron at some position and time. So the little kind of procedure is you solve this equation. It's like a boundary value equation for some problem, like the two-slit experiment. Calculate psi squared at the right place here. In our case, we would, oh, I jumped ahead, sorry. We would do it at the wall, and that would give us this probability distribution. Any questions? Is it all clear? That's kind of the essence of quantum mechanics, okay? So, and I've just given you one procedure. There's a lot to learn, but this is a start. Now, why quantum? Does anybody know why quantum? Okay, the people, okay. Why quantum? I just told you it's a wave. Yeah.
It's because of the multiple possible states, right?
Yeah, that's correct. That's correct. But let's even get at why. Because what did I describe? I described that you're solving a wave equation, right? Now, let's say for the sake of argument, I put a particle in a box, and the particle hates the walls. Its probability of being at the walls is 0. So to create a constructive wave, I need an integer number of wavelengths to fit. Okay? Now here you can see I have 1, 2, 3. Okay? Now let's say I wanted to include 4. Would that be just a little continuous change of the wavelength, or would it be a jump? A jump. Thank you. It would be a jump. And let me say this, even though, we're going at light speed here, this is a derivative operator in space, and it's the kinetic energy. So what that translates to here is that it's a jump in energy. So you get discrete energies when you confine electrons. That's the discrete energies you were mentioning. Let's say we do the same thing, and Bohr did this way back when, with an atom. You have a nucleus, you have the electrons spinning around, we got 3 little lobes. You've got to have the integer number of wavelengths go around the circumference to create a coherent wave that doesn't just, interfere with itself. Well, what if we wanted 4 lobes? Once again, we would jump in the radius, and we would jump in energy. Because just think, this is the potential energy between an electron and the nucleus. So we would get another jump in energy. So we naturally, just when you confine a wave, just like with a string or even very basic stuff, when you confine a wave, you'd get discrete, and you can get discrete energy levels, for example. Any questions about that? Discrete states, discrete numbers of the wavelength takes discrete values. Any questions? Yeah.
You mentioned like jumps, like you want to do like any 4 5, like energy jumps like a movie. So like if you think about valence electrons, it would be like that, like S.
Yep. Yeah, that's exactly right. In fact, just a very quick note, I think a lot of the physicists in the audience have done this. It's actually amazing. When you solve this equation for the hydrogen atom, and you just have a 1/r potential, the whole periodic table comes alive. You actually, the S and P, all these orbitals, these are angular momentum states. In fact, they're spherical harmonics. You get spherical Bessel functions and spherical harmonics that exactly tell you how chemistry works. And it's a fun homework problem to do. So this describes, so let me also mention along the way, like we're going to discuss what are the killer applications in quantum computing. Solving this beast, it gets very hard when you start to get to multi-electron systems, when you start to get to real materials, and particularly strongly correlated, like electron systems or strongly correlated systems, that we don't do well with. We do pretty well now with weakly correlated systems. But so this itself is a killer app of quantum computing. I'm going to mention killer apps along the way. This is maybe one of the top, if not the top. Okay, so any questions? We doing good so far? Okay, great. So how do we use this to build a quantum computer now? What the hell is a quantum computer? Pardon my language. Okay, so what we do, this is a little toy that I love. I just love this little schematic. This is a little toy schematic of a Josephson junction circuit. This is the basis of IBM and Google quantum bits, qubits. So basically, in a very crude, rudimentary sense, what you're trying to do, you have these confined, whatever, here it's superconducting currents or whatever, but you have them confined, and once again, they form discrete energy levels, okay? What you want to do is basically isolate 2 that you can manipulate. The lowest one is, let's say, the ground state, and the next one up is just the one excited state above. That's it. The 0 state, we're going to call the ground state 0, state of the qubit. The excited state, the 1 state of the qubit. And what you strive to build, if you're, let's say now here at IBM or Google, and then Olivier's doing with photonic quantum computers, is you manipulate this system here in the case of superconductors, you give it microwave pulses, and that's going to manipulate the state of the qubit in a way that I'll describe next. Okay? But this, in essence, is how you make use of these quantum properties. This is the beginning of what you try to engineer. You try to first create a qubit where the energies are isolated. Any questions? Yeah. The basic idea behind the picture is, yes, you'll still have energy levels above, but what you don't want is when you give it a microwave pulse, you accidentally throw the state into a third state, and that's not my design. My design is that I'm always between 0 and 1. Does that answer the question? Yeah, that's the essence of, that's what the cartoon's trying to portray. Okay, we're doing good. So when you zap the state, okay, what can you do? What ends up happening? Well, you can put the state into an arbitrary superposition. I can start with the 0 state, give it a microwave pulse, and then I can end up in this state, which is some coefficient times the 0 state plus some another coefficient times the 1 state. Okay? Now, it turns out that the way you should think about this is that the 0 state is a solution of the Schrodinger equation, of some Schrodinger equation. The one, for that circuit that I showed you before, the 1 state is also a solution of that Schrodinger equation. Now, what property did the Schrodinger equation have that I mentioned before that is relevant here? It's linear. Therefore, a linear combination of these two is also a fair solution of the Schrodinger equation. Okay? And hardware developers can zap a qubit and put it in some state like this. Okay? Now, how do we interpret it? What's the rule that I mentioned before that allows us to interpret things regarding the Schrodinger equation? This guy's name. Anybody remember? What rule? Whose rule? Born. The Born rule. So how do we interpret psi again? I've zapped the qubit into this state, so when I measure it, we apply the Born rule. So the probability of measuring the 0 state is alpha squared. The probability of measuring the 1 state is beta squared. Now, it turns out what you get for free is, because this is a solution of some Schrodinger equation, the Schrodinger equation is an eigenvector equation. So the 0 states, their inner product is 1. The 1 states, their inner product are 1. But the 0 with the 1 and the 1 with the 0 is 0. So if you remember your linear algebra, this is what's called an orthonormal basis. Okay? And I can just act to calculate this probability. I can project the 0 state. I can calculate the inner product with psi. With the inner product of 0 with 0 is 1. The inner product of 0 with 1 is what? 0. So, and then I take the square of this, I get alpha squared. That's the probability of measuring 0. The probability of measuring 1, we can go through the same exercise, we get beta squared. And it turns out the sum of these coefficients have to be 1, because those are just the probability, there's only 2 states. So I can only measure 0 or 1. So the sum of the coefficients have to sum to 1. Okay, any questions about this? No? This is the essence of a single qubit. Okay? Now, but what about more than one? Well, first we're going to stick with 1 qubit. Okay. So now, how do we make use of this? Like, what do hardware designers do, and what do algorithm developers do when we work? So hardware designers have to come up with very specific gates, like this Hadamard gate. This is just a specific zap, okay? They have to tune their microwave pulses in their system so that when a 0 comes in, what comes out is this 0 plus 1 divided by square root of 2. What's the probability of detecting the 0 state here? If I measured this, if I measure this, what's the probability of detecting the 0 state? 1/2. So the square of the coefficient. The probability of detecting the 1 state is 1/2 as well. And does 1/2 plus 1/2 equal 1? Yes. So another critical feature is you're always preserving the probability. You have no choice. And as a consequence, it just turns out the kinds of gates that these are unitary gates. They're unitary transformations of these vectors, okay? They preserve the length of the vector, all right? Just gonna say it so that it's out there and if people use that lingo. Now, when you come in with a 1 to a Hadamard gate, you get 0 minus 1. In general, the alpha and beta can be complex numbers, okay? And that includes just negative real numbers, okay? Any questions? Okay, great. Now, what about 2 qubits? Okay, this is one of the most important 2-bit gates. It's called a CNOT gate. Okay, so let's say x is 0. Okay, these are 2 qubits now. Let's say x is 0, okay? If x is 0, it will simply go on as 0, and y will go on as is if x is 0. In other words, if let's say y is 0, this will continue on as 0. But if y is 1, it will continue on as 1. But if x is 1, okay, then y is going to flip. So let's say x is 1. If y is 0 and it flips, what is it here if it flips? Started out 0, flips, what is it here? It's 1. It flipped. And what if it started out as 1 and it flipped? So again, just to summarize, if it starts out at 0 here, this will always, like if it's 0 here, it will be 0. If it's 1, it's 1. This does nothing to this qubit. But this qubit manipulates the second qubit. If this is 0, y passes on as is. If it's 0, this is 0. If it's 1, this is 1. But if this is 1, the qubit flips. So if it's 0, this flips to 1. If this is 1, this flips to 0. And that's the truth table here. Any questions? That's a 2-qubit gate. Now, I'm going to show you a tiny quantum algorithm, a tiny quantum circuit that just with these 2 gates executes something pretty profound. So what we do when we analyze these circuits, one thing you can do is you just kind of draw a line at the different spots and you go, okay, what is the state at every part of this circuit, this computation? Okay, so this is the first qubit, this is the second, this is size 0. So I'm just going to call the first qubit 1, the one on the left here, the second qubit here, the one on the right. It just starts out as 0, 0. Any questions about that? Pretty simple. Now, the first qubit undergoes a Hadamard operation. Second qubit, when we get to this stage, nothing. Okay, so what's the Hadamard? Do people remember what happens when you come in with a 0? Quick, does anybody remember what it is? Say it out loud. 1 over square root of 2.
It's 1 over square root of 2, the 0 state plus the 1 state.
Plus the 1 state. Look, just the 1 state is manipulated here, okay? The first qubit, you see you have the 0 state plus 1. This other guy stays the same. Everybody with me? All right, here we are. So now we're here. Great. Now we go through the CNOT gate. Okay, so when we go through the CNOT gate, the first qubit is 0. So what should happen to the second qubit? Stay the same. And it does. 0. But what if the qubit is 1? What happens to the second qubit? Flips. 1. Okay, and this now creates a profound state that we talked about before. And it's actually pretty simple. This is an entangled state. In some sense, a maximally entangled state. And all that means is, let's say I had a measurement here. And I measure 0 for the first qubit. What's the probability that I would measure that, by the way? Look at this. 1 over square root of 2. What do we do to the coefficients? 1/2. Measure 0, probably 1/2. But then what do I get here? For sure. If I measured a qubit here, I'm Alice. What does Bob see? For sure. Come on. Look at the state. I like that you tried. Thank you. This is the first qubit. What is the second? Well, just read it out. It's the same. What if I measure a 1? What am I guaranteed to get? A 1. They're perfectly correlated. Okay? And this state is a profound state. Like, this is the Einstein-Rosen-Podolsky state. This started a whole 9 yards. The 2022 Nobel Prize is based on basically assessing states like this in a Bell test. And Einstein, this is what Einstein called spooky action at a distance. We're not going to get into what's weird about it. But again, what I want to emphasize at face value, this is pretty simple. They're just perfectly correlated. You couldn't get more simple than that. Okay? It's hard to comprehend when you reconcile it with our everyday life, with the real world. But I don't want to get into what's weird. Okay, so where does the power come from? I've just showed you 2 qubits. So, but in general, with even 2, I can have the following 4 states. I can have, read it out for me, if anybody. I just showed you 2 of them. Are there any others? If I have 2 qubits, are there any other possible states that you can imagine? And what else? Yeah. 4 states, okay? And each one has a coefficient. And what does the sum of the square of the coefficients have to equal? Yeah! We're doing it. We're there. Okay, so what if you have 3 qubits? How many states? 8, and that's on the board right here. Okay, what if we have 4 qubits? Okay, and you can see I'm reading it out. Okay, so even at 32 qubits, Fred, I can start analyzing the whole genome, 1 base at a time in a quantum computer. Okay, let's say I wanted to let's say I was doing a genome, like I had genomic data that is just genome data, and then I added RNA-seq, but I wanted to analyze it at a single base level. I just have to add 1 qubit more, just to add RNA-seq, not another 3 billion registers. And you can see it's exponential. This is one of the superpowers of a quantum computer, without a doubt. Okay? So basically, you've probably heard Google, IBM, they've simulated random circuits with on the order, I think, of 50 qubits, something like that. And basically, even at that scale, 2 to the 50, like the Oak Ridge supercomputer cannot, it would take a gazillion years. Now, it wasn't a useful calculation. It simulated a quantumly correlated random circuit. But you couldn't do it with a classical computer in any kind of reasonable time. So even 2 to the 50, and we're planning on going way beyond that. Okay, so the state space is vast, and we call this a Hilbert space. All that is a vector space of complex numbers. It contains an inner product, and the states, when you take the inner product of a state with itself, that's well defined. Blah blah blah. Okay, but that's what you call this. You get into this huge so-called Hilbert space. Okay, now. Now I'm just going to give you an abstract sense of what is a full quantum algorithm. Okay, and I have that on the board, all right? So here, I've just, for the sake of, simplicity, I have how many qubits? I got 3 qubits, okay? Starting them out at the 0 state. I'm explicitly showing what happens with 3 Hadamard gates at the 1 state. Turns out you just get an equal superposition. Is this normalized, yes or no? Why? 1/√8. So I have to take the sum of the squares, and so that's just going to be 8 divided by 8 gives me 1. So this is a normalized state. Now that's the way I start. Now, what's going to happen is U is actually a quantum algorithm. It's a set of gates, like I've shown you. There are more gates than I'm showing you. I will show you more gates. But there's plenty of gates at your disposal, okay? But right now, we're just going to call it a unitary transformation. And the nature of a quantum algorithm is you're coming up with a series of gates to execute to get some answer. Okay, so we're going to apply the same gate multiple times. And I will say among the top performing algorithms that have definite quantum advantage work like this. So basically, you apply U, and now I'm just showing the coefficients kind of a little more abstractly with arrows, okay? So here's my psi1. This value is 1 over square root of 8 for each one. They're amplitudes. Okay, are you with me? Everybody with me? Now we go to psi2. Okay, we've acted on this algorithm. It's a clever algorithm. Okay, and I know ahead of time that this is the answer. I just know ahead of time. But when I design the algorithm, normally I don't know which one it's going to give me, but I've designed the algorithm cleverly so it gives me an answer that's important to some problem. Okay, so now at psi2, what happens is you can see. Can you see this one going up? Can you see this one went up? What happens to the other ones if this one goes up? They get smaller. Why? They have to. Why? They have to sum to 1. So that's constructive and destructive interference. Okay, so I'm going to do this again. Okay, I'm going to beat these down to the ground. These are the wrong answers. This is the right answer. Okay, so I'm just going to do this again. All right, so now I'm going to apply this guy, psi3. This is bigger. These are smaller. And then I do it again. This one's way big. This one's way small. And then I make the measurement. What do you think I'm going to get with high probability? The right answer. So Grover's algorithm does a structured search of an unstructured database. Classically, that would be, it would take n over 2 steps of a database the size of n. Grover's does it in square root of n time. That's one of the classic algorithms. Shor's also does it. It's a much more complicated algorithm to describe, but if we have a sufficiently powerful quantum computer, it would basically break our encryption. Okay, it allows you to figure out the prime factors of a big number, and that's the source of our RSA code. So if we built a sufficiently powerful quantum computer and executed Shor's algorithm, we could decrypt documents. People could go into your bank account. Blah blah blah. Okay. So this is one of the most powerful algorithms, and I'll be honest, I believe this is one of the drivers of government funding because of obvious reasons, like the NSA. Yeah. They can be single and 2, but yeah, and they're you can show that they're a universal gate set. So basically, a universal quantum. I'm glad you asked that question. A universal quantum computer, basically, just think. Let's say I had 3 qubits for right now, and that was my quantum computer. A universal gate set for a 3-qubit quantum computer can touch any possible state. So I can touch any possible complex number coefficient with that gate set. Okay, and all you need is C naughts and a few other gates, and you're done. Does that answer your question? Yep. It's composed of single and 2-bit gates usually. Yep. Yep.
Is that algorithm like stronger than like the binary search or like search?
Well, linear, yes, because it's square root. But let's just say this. What's impressive? Computer scientists actually, before they knew about this algorithm, I learned this from a John Watrous video at IBM. Computer scientists actually proved that the fastest you could do that unstructured search of square root of n without knowing that a quantum computer algorithm would be the one that could do it. That's a real testament to kind of the way they estimate complexity in algorithms. So I knew I would not get to the other parts. So here, just as a quantum machine learning application, but I'm going to skip through it. My goal was to really give you a sense of quantum computing. So I'm going to end with 2 minutes, right? We're sub 2 minutes. Okay, so where are we? Basically, I'm not going to read all of this, but I'll just give you a couple of thoughts. We have to drive down the individual qubit error for quantum computers to work, and we're getting there. But you have to drive it down. But the strategy for most quantum computers is not to get the physical qubit error rate down to some ridiculously low number. And you have to get to these numbers basically, you can think of them as however many gate operations you have, you have to have your single gate operation error low enough so that you don't get an overall error. So you need errors way down into like 10 to the minus 12, at least 10 to the minus 6. And the strategy with classical computers we dedicate extra bits to identifying and correcting bit errors in a bit stream. That is currently done with classical computing. There are very clever algorithms to do that. Quantum computing has the same thing. You dedicate extra physical qubits to identify and correct qubit errors. Those are called logical qubits. So what people are pursuing is improving the individual physical qubit error, but then building logical qubits that now can function at very low error rates. Okay? And with that, I'll just end. Oh, yeah, absolutely.
So you talk about how you are going through some number of gate operations to reduce the probability of observing these other states, right? Because it still is a probability distribution. You basically have to arbitrarily go through some number of gates in order to drive that probability low enough.
When you say, yes, there's, yes. So like, for example, with Grover's, it turns out there's a specified number of operations you have to perform. Actually, if you don't hit the right number, it actually starts to go wonky and get the wrong answer again. So yeah, but you can pre-calculate what that number is. Okay. Yeah, and that's correct. And there's another important thing to say is that to get statistics on these coefficients, what you do this with IBM and other quantum machines. What you do is you run the algorithm many times to get statistics, because you get a probability each. You get one outcome like 001 with some low probability. You'll get this one with high probability a lot. But what you do is you run the circuit many times, and then you'll actually get a good estimate of the coefficient squared, each one. Okay? Any other questions? Yeah.
When you showed like the LC circuit,
Yep.
Was the idea there, like the quantum part, is the idea there that it could only resonate at certain frequencies?
Yeah, it's actually, I'm actually not an expert on transmon qubits. I did do an essay in my condensed matter class on Josephson junctions. So you see this circuit element right here, the Josephson junction. So this is a superconducting circuit, and the Josephson junction is an air gap. And what Josephson showed is not only do you get a current across the air gap, you get a superconducting current across the air gap with no resistance. And it has all these exotic properties, like when you apply a DC field, you get an AC output, and you get funny steps if you put in an AC field. And this actually is, this kind of circuit, it was explored and is the source of this year's Nobel Prize. So what they did was that, and it's the kind of the precursor of the superconducting qubit. What you can show is that this whole thing actually, so you know how I'm writing wave functions and stuff? It turns out that in a superconductor, you can think of all the electrons as pairing up and forming almost like a boson, and piling up into a state to create a macroscopic quantum state. And what they showed was that this is many, like billions of electrons. They showed that actually tunnels in like a quantum electron, like a simple electron. So they showed that it had fundamental quantum properties. That was yeah. I don't know if that answered. Yeah.